So, good afternoon, sir. Good afternoon, everyone. Our group will present two laboratory reports. First is the standard test method for compressive strength of hydraulic cement mortars using 2-inch or 50 mm cubic specimens. We have three objectives here. The main objective of the lab experiment is to determine the compressive strength of hydraulic cement mortars using cubes of material that are 2 inches on a side through conducting compression tests. Second, to determine that the mortar mixture as delivered on site meets the requirements of the specified strength in the job specification. And lastly, to verify whether the cement conforms to ASTM specifications and whether it will be able to develop the concrete of required compressive strength. Introduction. Concrete, as we all know, has become part of our daily lives. Since concrete is mostly the main material sa paggawa sa construction. Nakikita natin siya na ginagamit sa roads, sa bahay, buildings, infrastructures, or any structure man yan. Concrete sa nadaanan natin from the past modules, concrete consists of cement, water, sand, and aggregates. So, hydraulic cement mortars are a combination of cement, sand, and water. Hydraulic cement mortars are similar to concrete, pero yung hydraulic cement mortars ay ginagamit siya to stop water or mga leakage sa concrete. ASTM issued a standard for testing hydraulic cement mortars using compressive strength. Yung ASTM na to is the ASTM 109/109M-02. Compressive strength. Ano nga ba yung compressive strength? Compressive strength test is one of the most compelling properties for mortar and cement. Bakit siya tinawag ng one of the most compelling properties for mortar and cement? Since pag gumagawa tayo ng concrete or mga structures, pag ginagamit natin yung concrete, gusto natin matibay siya, durable, and safe. So, kung safe siya, matibay siya. So, paano nga ba nangyayari itong compressive strength test? Compressive strength test is happened on a hydraulic pressure or hydraulic press. Hydraulic press pose a pressure on a test specimen which is executed in a 2-inch or 50 mm cube specimen until it reaches failure.
In standard test method for compressive strength of hydraulic cement mortars, here are the instruments used. First is the weighing devices. The weighing device shall be evaluated for precision and accuracy at a total load of 2,000 grams and shall conform to the requirements of specification C1005. Next is the glass graduates, preferably large enough to measure the mixing water in a single operation. These graduates shall be subdivided to at least 5 ml, except that the graduation lines may be omitted for the lowest 10 ml for a 250 ml graduate and for the lowest 25 ml of a 500 ml graduate. Next is the specimen molds. The molds shall have not more than 3 cube compartments and shall be separable into not more than 2 parts. For the 2 inches or 50 mm cube specimens shall be tight-fitting. Cube molds shall be checked for conformance to the design and dimensional requirements of this test method at least every 2.5 years. Next is the mixer, bowl, and paddle, an electrically driven mechanical mixer of the type equipped with paddle and mixing bowl as specified in practice C305. Next is the flow molds used to determine the flow of hydraulic cement mortars and cement pastes, conforming to the requirements of specification C230 or C230M. Next is the tamper, a non-absorptive, non-abrasive, and non-brittle material such as a rubber compound having a Shore-A durometer hardness of 80 positive negative 10 or seasoned oak oud, rendered non-absorptive by immersion for 15 minutes in paraffin at approximately 392 degrees Fahrenheit. Tampers shall be checked for conformance to the design and dimensional requirements of this test method at least every 6 months. Next is the trowel, having a steel blade 4 to 6 inches in length with straight edges, used for digging, applying, smoothing, or moving small amounts of viscous or particulate material. Next is the moist cabinet for curing mortar and concrete test specimens, has 11 feet squared capacity and heated. Triple pane glass door to minimize condensation for observing of specimens. Conforming to the requirements of specification C511. Next is a testing machine. It is used in materials to determine the properties of a material. Machines have been devised to measure the tensile strength, strength in compression, shear, and bending, ductility, hardness, impact strength, fracture toughness, creep, and fatigue.
Good morning everyone. So for the activities, just like what Mr. Kos said, it's just the procedure itself. So I'll just show you the video that I searched para mas makita at mas madali nating maintindihan kung paano sinasagawa yung experiment. So yung pinakaunang gagawin, of course, ipiprepare muna yung mga gamit na gagamitin for the lab activity. So, para sa paggawa ng mortar, kakailanganin natin ng Ottawa sand, cement, and of course, yung water. After the preparation, pwede na natin simulan yung lab activity. So, first, lalagay natin si 242 cc of water dun sa mixing bowl. Then, after that, pwede nang ilagay si 500 grams of cement. So, after malagay yung cement, pwede na siyang haluin at a slow speed for 30 seconds. After 30 seconds, pwede nang i-add si 1,375 grams of Ottawa sand over a 30-second period while continuing to mix at a slow speed. So, yung paglagay ng sand is hindi siya isang bagsakan. So, dahan-dahan siyang nilalagay. After 30 seconds, papalitan yung mixer setting into medium speed and imimix siya ulit for another 30 seconds. After 30 seconds, stop muna si mixer and hayaan lang muna yung mortar for 90 seconds. During the first 15 seconds, pwedeng scrape down muna yung mga naipong mortar dun sa gilid ng bowl. So, habang naghihintay ng remaining seconds, pwedeng prepare muna yung cube molds or yung cube compartment. After 90 seconds for final mixing ng mortar, imimix siya ulit for another 60 seconds at medium speed. Upon completion of mixing, start ng i-mold yung specimens by placing a 25 mm or 1-inch layer of mortar dun sa cube compartments. After that, itatamp na yung layer ng mortar in each cube compartment, of course with hard rubber tamper. 32 times siyang itatamp within about 10 seconds. May pattern yung pag-tamp ng mortar. So, bale, ito yung sinusundan na pattern. So, para mapuno yung cube molds, mag-a-add ulit ng another layer ng mortar and ulitin lang ulit yung tamping procedure. At this point, nakikita natin yung sobrang mortar. Andun na siya sa top ng mold. So, ang gagawin lang dyan is kakatin lang yung sobrang mortar using steel trowel or yung ginamit niyang pang-tamp. After that, pwede nang ilagay si completed mortar cubes dun sa moist closet na hindi natutuluan ng tubig for between 20 to 24 hours. After 20 to 24 hours, ilalagay na si mortar cubes dun sa saturated lime water bath until ready na siya for testing. Tapos yung lime water, kailangan siyang palitan periodically para mapanatiling malinis. Lahat ng specimens is itetest within a specified time period.
So now guys, let's proceed to the formula to be used in order for us to simulate the calculation. In this given report, we will be using two formulas. As you can see, the first one is quantity FMI is equals to P all over A, wherein P will serve as the maximum load in Newton unit. Then A is the area of loaded surface with the unit of square millimeter. Thus, having this formula will give us the compressive strength of a given specimen in megapascal or MPa. On the other side, you will be seeing the second formula. This formula will be used to determine the average of the compressive strength of the specimen, which equals to summation of FMI all over N, wherein FMI again is the compressive strength and N is the total number of specimens. These formulas will be utilized under 3 trials for us to definitely observe the accuracy and precision of the results. More so, this will also assist the gathered results, specifically the second formula, to have the comparison each trials, hence provide explicit conclusions.
Now we go to the data and results obtained through proper procedure and proper calculations. In Table 1, it shows the test results for the 7-days age test. All 3 samples have an area of 2,580 mm squared, but they differ in load at failure. In Sample 1, it has a load at failure of 12,731 Newton and leads to a compressive strength of 4.92 psi. In Sample 2, it has a load at failure of 12,641 Newton and leads to a compressive strength of 4.90 psi. And in Sample 3, it has a load at failure of 12,327 Newton and leads to a compressive strength of 4.78 psi. The average compressive strength of a hydraulic cement mortar at 7 days is 4.87 psi. In Table 2, it shows the test results for the 14 days age test. All 3 samples have the same area of 2,580 mm squared, but also differ in load at failure. Sample 1 is a load at failure of 15,459.06 Newton and leads to a compressive strength of 5.99 psi. Sample 2 has a load at failure of 15,349.8 Newton and leads to a compressive strength of 5.95 psi. And in Sample 3, it has a load at failure of 14,968.5 Newton and has a compressive strength of 5.80 psi. The average compressive strength of a hydraulic cement mortar at 14 days is 5.91 psi. Table 3 shows the test results for the 28 days age test. All 3 samples have an area of 2,580 mm squared, but also differ in load at failure. Sample 1 is a load at failure of 18,187.14 Newton and leads to a compressive strength of 7.05 psi. Sample 2 has a load at failure of 18,058.58 Newton and leads to a compressive strength of 7 psi. And Sample 3 has a load at failure of 17,610 Newton and has a compressive strength of 6.83 psi. The average compressive strength of a hydraulic cement mortar at 28 days is 6.96 psi.
The next one is on how we get the computed value using the formula. For test results for 7 days age test. In sample 1, we are given of P equals to 12,731 Newton, A equals to 2,580 square millimeter. To get the compressive strength of specimen, we use the maximum load over area of loaded surface equals 12,731 Newton over 2,580 square millimeter. We get the 4.393 psi. For sample 2, 12,641 newtons over 2,580 square millimeter, we get the value of 4.90 psi. And in sample 3, 12,327 newton over 2,580 square millimeter, we get the value of 4.78 psi. To get the average compressive strength, For test results for 7 days H test, we use the formula of summation of compressive strength of sample 1 to sample 3 over the number of the specimen equals to 4.93 plus 4.90 plus 4.78 divided by 3. We get the value of 4.70 psi or 0.03 megapascals. The second one is for the test results for 14 days age test. For sample 1, 15,459.06 Newton over 2,580 square millimeter, we get a value of 5.99 psi. In sample 2, 15,349.8 over 2,580 square millimeter, we get the value of 5.95 psi. And for sample 3, 14,968.5 newtons over 2,580 square millimeter, we get the value of 5.80 psi. To get the average compressive strength of for test results for 14 days age test, the summation of sample 1 to sample 3 over the total number of specimens 5.91 plus 5.95 plus 5.80 divided by 3, we get the value of 5.91 psi or 0.04 MPa. And lastly, for test results for 28 day age test, in sample 1, we use the 18,187.14 newtons divided by 2,580 square millimeter, we get the value of 7.05 psa. On sample 2, using 18,058.58 newtons over 2,580 square millimeter, we get the value of 7 psi. And for sample 3, we use 7,610 newton over 2,580 square millimeter, we get the value of 6.83 psi. To get the average compressive strength of test results for 28 days age test, the summation of compressive strengths of sample 1 to sample 3 over the total number of the specimen equals to 7.05 plus 7 plus 6.83 over 3, we get the value of 6.96 psi or 0.05 megapascal.
Drawings and figures. At the top left corner, you can see the three main ingredients in making a concrete. Below that is weighing balance. It is the tool to get the exact measurement of cement and sand. And to the top right is cement cube mold, and lastly is compression machine.
Hello everyone, my name is Leonard Luna. I'm about to report the possible source of error when performing the experiment. In general, we have three types of error. One is natural error, two is instrumental error, and lastly is personal error. Here we listed some source of error. First is a proper tampering techniques. It is assumed that the lower compressive strength of sample 3 is due to poor tampering technique mentioned previously in test procedure. Temperature. It is important to keep track of room temperature because it might be a source of error if it is not properly maintained during the experiment. Third, human error. It is expected that the mortar sample would have a higher average compressive strength. This could have been a human error related to 10.4.1 of ASTM C109, which involved mixtures of sample. Next is expertise of the worker. It can be a possible source of error if the worker didn't master what he is doing. that also leads endangered or misuse of the materials. Lastly, defective equipment. It could also be a possible source of error if the equipment isn't working properly. That's all. Thank you.
Conclusion. The following conclusions imply that compressive strength should be substantially enhanced. First, water ratio affects the compressive strength of mortar. A lower ratio results in greater strength and durability, but may make the mix difficult to work with and shape. If there is too much water, the sand and aggregate components will separate from the cement paste. Water-cement ratios ranging from 0.45 to 0.60 are more commonly used. Lower ratios are used for higher strength concrete along with plasticizer to increase flowability. A mix with too much water will shrink more as the excess water evaporates, resulting in internal cracks and visible fractures, lowering the final strength. Second, segregation of graded standard sand. It should be handled in a way that prevents segregation because variations in sand grading cause variations in mortar consistency. And also, it should be taken to avoid the formation of sand mounds or crests in the sand, down which the coarser particles will roll. Gravity drawing devices for removing sand from bins should not be used. And lastly, weight percent of cement. It has a significant impact on the properties of both fresh and hardened concrete if the cement did not weight properly. In addition, low strength development or excessive shrinkage may occur if the proper range of cement is not present in the mixture, resulting in premature deterioration.
The purpose of this lab experiment was to determine the compressive strength of hydraulic cement mortars using cubes of material that are 2 inches on a side through conducting compression tests. It also aims to verify whether the cement conforms to ASTM specifications and whether it will be able to develop the concrete of required compressive strength. The data gathered is within the guidelines of ASTM International Standards, which is issued under the fixed designation C109 C109M. By performing ASTM C109, we can determine a water or cement ratio to meet certain specifications or requirements required for a mixture.